hash tables. If you only ever properly learn one data structure, make it this one. Almost every programmer alive uses one every day, and most could not tell you what it does underneath.
Let's start with the problem, and it is not a theoretical one. You have 200,000 users sitting in an ordinary list. Somebody signs in, and your code has to find one of them by email address. So you do the obvious thing. You loop over the list and compare every row until you hit a match. This code is correct. On my machine, it takes 4.4 milliseconds. 4 milliseconds is nothing, right up until you are handling 2,000 sign-ins a second. At that point, you are asking for 8.8 seconds of processor time every second, and a second is all you get. Nothing crashes. Nothing appears in your logs. The server just quietly stops answering.
So let's name the subject. This is hash tables. You will also hear them called hash maps, dictionaries, or associative arrays, depending on the language you grew up in. Same structure, 4 names. In Python, it is the dict, and it is also the set. Now, what does the area actually cover? 4 things, and that is the whole syllabus. The hash function, which turns a key into a number. The bucket index, which folds that number down to one slot in an array. Collisions, which is what you do when 2 keys land on the same slot. And the load factor, which tells the table when it has to grow. What this is not, it is not password hashing, and it is not encryption. Same word, completely different job.
Before any code, here is the machine that makes it obvious. Picture a mailroom with a wall of numbered slots. The slow version works like a list. To file a letter, you walk along the wall looking for a free slot. To fetch it back, you walk the wall again, reading label after label. 200 slots means up to 200 looks. Now add one rule. Take the name written on the envelope and run one small calculation on it. Count the letters, add up their codes, whatever, as long as it is the same calculation every time. That calculation gives you a slot number. So filing becomes do the sum, walk straight to that slot, done. And fetching is the same sum, so it lands on the same slot. You never look at the other slots at all. That is the entire idea. The speed does not come from searching faster, it comes from not searching. Let's look at real code, starting with the version you would write first. Load the users into a list. Find user then loops over that list, comparing one email per row until it matches. On average, that is 100,000 comparisons, and in the worst case, all 200,000. And I want to be clear about something. There is nothing bad in that code. It is correct, it is readable, and for a list of 20 items, it is the right answer. The only thing wrong with it is the shape of the cost. Double the users, and you double the work, forever. That shape has a name, big O of N, and changing it is the entire reason hash tables exist.
So how big is the difference? I measured it. Scanning the list of 200,000 rows, 4.4 milliseconds. The identical lookup out of a Python dictionary, same data, same machine, 71 nanoseconds. A nanosecond is a billionth of a second. That is roughly 62,000 times faster, and the gap widens every time you add a user. The important part is why. It is not that the dictionary is written in faster C code. They both are. It is that the list looks at 100,000 rows, and the dictionary looks at 1.
So let's build one, not import one, build one, because it is smaller than people expect. First line, buckets, is a list of 8 empty lists. That is our wall of slots. Second line, in counts how many keys we hold, and it matters later. Now the important one, and honestly, this is the whole video. Underscore index takes a key and returns hash of key modulo the number of buckets. Hash is built into Python. Hand it a string and it hands back a large integer. Modulo 8 folds that integer down into the range 0 to 7. Key goes in, slot number comes out. That single line is the hash table. Everything else here is bookkeeping. And you can see it working in get. Get calls underscore index once, steps into that one slot, and compares only the key sitting in there.
Let's watch 8 names go in. Grace hashes to about 98 million. Modulo 8, that is 0. So Grace goes in slot 0. Barbara lands in 1, Ken in 4, Linus in 7. Now keep your eye on slot 0. Alan hashes to a completely different number in modulo 8 that is also 0. So is Edsger. 3 different keys, 1 slot. That is a collision, and it is not a bug or a sign of a bad hash function. It is arithmetic. You are folding billions of possible numbers into 8 slots, so of course some land together. Slot 6 has 2 as well, and slots 2, 3, and 5 got nothing at all. Both of those are normal. So the question is never how to avoid collisions, it is what you do when one happens.
And this is what you do. Here is set. It works out the slot exactly like get did. Then it walks the entries already in that slot. If it finds this exact key, this is an update, so it swaps the value and returns. Otherwise, and this is the line that matters, it appends the new pair onto the end of that slot. So a slot does not hold one entry. It holds a little list of entries. That is called chaining, and that one append is the whole of it. Here is a real run. Slot 0 holds 3 pairs, Grace, Alan, and Edgar, sitting together. And asking for Alan still comes straight back, because it went to slot 0 and compared 2 keys. 2 comparisons, instead of 200,000.
That only works while the chains stay short, and there is a number that controls it. It is called the load factor, the number of keys you store divided by the number of slots you have. 8 keys in 8 slots is a load factor of 1. Here is the way to think about it. The load factor is the average number of keys sitting in a slot, which is the average number of comparisons a lookup does. So it is not a tidiness measure. It is your lookup cost, written as one number. I measured it with 100,000 real keys. At 0.75, the average chain is 1.4. At 2, it is 2.3. At 8, the average chain is 8, and the longest is 21. It gets slower smoothly, which is exactly why nobody notices in time. This is why the textbook writes big O of 1 as amortised, average case. The load factor is not a fact about your data. It is something you keep down deliberately.
Which is what these 4 lines do. At the bottom of set, after we have added the pair and bumped the counter, we check one thing. If n divided by the number of buckets is greater than 0.75, in other words, if the table is more than 3/4 full, we call resize. And resize is short. It keeps the old array, builds a new one with twice as many slots, then walks every pair in the old one and inserts it into the new one. Here is the part people get wrong. It cannot just copy the pairs across into the same positions. Underscore index divides by the number of buckets, and that number has just changed, so every key belongs somewhere different now. Reinserting all of them is called rehashing.
And here are the same 8 keys straight after that resize, 16 slots instead of 8. Look at Edgar. Modulo 8, he was slot 0, and modulo 16, he is still 0. But Grace, who was also slot 0, is now slot 8. Same key, same hash, different slot, purely because the divisor changed. And look at the result. The chain that was 3 deep is now a 1 and a 2. That is all a resize ever does. It buys the chain's room by making the divisor bigger.
Our toy resolves collisions by chaining, but that is not the only way, and you use both every day without noticing. Chaining is what we built. Each slot holds a little list, and a collision just makes one list longer. Simple to write, simple to delete from. The cost is that every entry needs a pointer, and chained entries end up scattered across memory, which your processor's cache hates. The other way is open addressing. There are no lists at all. Every entry lives directly in the array, and when your slot is taken, you move on to another slot by a fixed rule. That is far friendlier to the cache. The catch is deleting. You cannot just empty a slot, because that breaks the chain of probes, so you leave a marker behind, a tombstone. Neither approach avoids collisions. Nothing does. So when does that famous big O of 1 stop being true? Here is the honest answer. Measured. 4,000 keys with an ordinary hash function. The longest chain is 4, and a lookup takes 0.4 microseconds. Now the same 4,000 keys with a hash function so bad that every one lands in slot 0. One chain, 4,000 entries long. That lookup takes 74.5 microseconds, 186 times slower. Same table, same keys, same machine, only the hash changed. Now think about that from the outside. If an attacker can work out your hash function, they can send you exactly the keys that all collide, on purpose, and turn your fast lookups back into slow scans. That is a real denial of service attack, and it is why Python randomizes the hash of every string each time your program starts. Which brings us back to the one you already use. Every dictionary, every set, every keyword argument in Python is a hash table. Same idea we just built, with 3 details worth knowing. First, CPython uses open addressing rather than chaining, and it grows the table at around 2/3 full. Second, since version 3.7, a dictionary keeps the order you inserted things in. That comes from a second, compact array of indexes sitting alongside it. It is not something hashing gives you for free. Third, a key has to be hashable, which in practice means immutable. Try to use a list as a key, and Python raises unhashable type, list. And here is my favorite. Hash of 1, hash of 1.0, and hash of true are all the same number. So a dictionary written with those three as separate keys is really a dictionary with one key in it.
Now the part interviews really probe, when is this the wrong tool? A hash table is unbeatable at 3 questions. Is this exact key here? What is the value for this exact key? Have I already seen this one? Ask it anything else and it has nothing for you. Give me every key between 10 and 50. It cannot. The smallest key? It cannot. Everything starting with the letters SM? It cannot. Sorted output? The nearest match? The next key after this one? No, no, and no. And that is not an oversight. Hashing deliberately destroys the relationship between keys. 2 keys next to each other in the alphabet get thrown to completely unrelated slots, which is exactly why a database index is a B tree and not a hash table.
And that brings us to the questions this unit unlocks, because every unit in this series ends here. Question 1. Why is a dictionary lookup big O of 1? The skeleton is, the key is turned into a slot number by arithmetic, not by searching. 1 hash, 1 array index, then a comparison against the handful of keys in that slot. And say the words amortized average case out loud, because the resize is the amortized part. Question 2. What happens on a collision? 2 keys fold to the same slot, and nothing is lost or overwritten. With chaining, the slot holds a list and the new pair is appended. With open addressing, you probe onto another slot by a fixed rule, which is what Python does. Question 3. What is the load factor and why resize? Keys divided by slots, which is the average chain length, which is the lookup cost. And a resize rehashes every key, because the divisor changed.
And 2 more, where most people stop at half an answer. Question 4. When is a hash table the wrong choice? When you need order, so ranges, prefixes, smallest, largest, sorted output. When the worst case matters, because one bad hash makes it big O of n. When memory is tight, or your keys are not hashable. And a complete answer names the replacement, a B tree, a sorted array, or a trie. Question 5. What makes a good hash function here? Deterministic, so the same key gives the same number every time. Well spread, so a small change in the key moves the slot a long way. And cheap, because you pay for it on every single operation. And it is not a cryptographic hash. Different job and far too slow for this one. If you can state the trade-off and then name what you would use instead, you have answered it. That is hash tables all the way down to the code. If it filled in a gap, hit like and subscribe, and the next unit will find you.